Hi, everyone. My name is Yichi. I'm a third-year PhD student at Cornell Computer Systems Lab, and I'm advised by Professor Zhiru Zhang. The paper I'm going to present is FracBNN, accurate and FPGA-efficient binary neural networks with fractional activations. This is a work in collaboration with Professor Deming Chen's group at UIUC. In recent years, for energy cost and security reasons, there is an increasing demand of deploying deep learning models on edge devices. For example, we want to deploy them on mobile phones, autonomous systems, smart IoT devices, and such. But there are stringent hardware constraints on this. Let's take a popular model, Resonant 18, as an example. An 8-bit version of the model has 93.5 million bits of weights and 1.8 giga MAC operations. If we want to deploy this model on an embedded FPGA board, such as Xilinx Ultra96 V2, the device itself has only 7.6 million bits on-chip memory capacity. This is 12x smaller than the model size, and it only has 360 DSPs and about 70K LUTs to handle the gigantic amount of operations in the model. So the small on-chip memory capacity and the limited number of computing resources have really made this problem very challenging. To address this problem, we can binarize the neural networks. In traditional convolutional neural networks, feature maps and weights are both floating point. But in binary neural networks, input feature maps and weights are binarized to either plus or negative ones. The output feature maps are therefore integer values. So the key differences between CNNs and BNNs are that the values are binarized. And because of this, we can compute the MAC operations in a more efficient way, which is using XNOR plus popcount operations. With these properties, the memory footprint and compute intensity of BNNs are low. This makes them very suitable for embedded FPGAs. Binary neural networks are competitive on small tasks such as MNIST and CIFAR-10. But one problem is it produces low accuracy in practice, especially on realistic datasets such as ImageNet. When the first time it is evaluated on the ImageNet dataset, the top one accuracy is only 36.1%. And from then, there's a whole line of works that is trying to improve the BNN accuracy. Here we select some of the milestones and show them in a timeline. In 2016, XNOR-net improves the top one accuracy by about 15%. And BRealNet in ECCV 2018 was the first BNN that employs shortcut connections in each conv layer. This pushes the top one accuracy to 56.4%. There's also Ensemble BNN that increases the accuracy, but is at a huge cost of model size. And recently, Real-to-Binary-Net shows that you can actually get 65.4% using a BRealNet-like model design. And most recently, ReactNet shows up. It demonstrates that by activation shifting and reshaping, you can get a top one accuracy of 69.4%. This number is already on par with the popular Resonant 18. However, there's still a gap between this BNN and compact floating point models such as MobileNet V2 that has 72% top one accuracy. In this work, we propose FracBNN, which is designed on top of ReactNet. We show that with fractional activations, we can improve the BNN accuracy to 71.8%. And this accuracy is much higher than Resonant 18 and some recent low-bit networks such as DRAC-DeltaNet. For the first time, we're able to achieve MobileNet V2 level accuracy with competitive model size. Another remarkable problem with the current BNNs is the resource inefficiency of the input layer. Existing BNN models require floating point or fixed point convolutions in the input layer. So we have to design a high precision input compute engine for the input layer alone. All the other binary layers share another binary compute engine. And these two engines are both instantiated on the resource-limited embedded FPGA. The bad thing is the high-precision compute engine costs 80% of the DSPs and 32% of the LUTs, but it cannot be reused by all the other binary layers. The huge resources taken by this high-precision input layer cannot be used to accelerate the main part of the network. This is a huge waste. So to make the resource utilization more efficient, we need to binarize the input layer. In this work, we propose FracBNN using algorithm hardware co-design. There are three main contributions compared to a conventional BNN. One, we managed to binarize the input layer with minimal accuracy degradation. We address this resource inefficiency problem by using a novel thermometer encoding. Two, we use fractional activations to further improve the model accuracy. Essentially, we're computing a sparse binary convolution to update the binary convolution results in the base path. Three, we implement the accelerator of FracBNN on an embedded FPGA and deliver its real-time performance. Now let's dive into the details. And first, I'm going to talk about the binary input layer. Directly binarizing the input layer incurs a large accuracy loss, and that's why prior works employ a high precision input layer. To figure out the reason, we take the regular RGB images and compute the convolutions using floating point weights and binary weights respectively. We want to see how closely these convolutions are related before and after binarization. It turns out that the Pearson correlation coefficient is only 0.34, indicating a weak correlation. The dots in the figure are supposed to be close to the diagonal line, but now they spread away. It means that if we only have 3 channels in the inputs, the binary convolutions will no longer be related to their floating point counterparts anymore. And that's why we're getting a low accuracy after binarization. So we need more channels in order to binarize the input layer. One natural method of enriching the channels and meanwhile having binary inputs is using the fixed point representation. In this way, we have 8x more channels. In prior works, it is called DBID, direct binary input data. However, experiments show that this will lead to an 8.3% accuracy degradation on the ResNet 20 BNN on the CFAR10 dataset. There's also prior work that first expands the number of channels and then again use the fixed point representation as the inputs. And turns out that even if the number of channels is increased to 256, there's also a 3.5% accuracy degradation, which is non-trivial. This tells us that simply using fixed point representations does not work. But why is that? We find that in a fixed point representation, each bit is associated with a certain weight. For example, the most significant bit 0 has a weight of 2 to the power of 7. The least significant bit here has a weight of 2 to the power of 0, so on and so forth. However, when we take this binary string as the input to the neural networks, the associated weight information is lost. The method is hoping that neural networks can automatically learn these weights back, but it is actually a very challenging task. To address this fundamental problem, we propose to encode the pixels using thermometer encoding. In a thermometer vector, there are only zeros or ones. The number ones is equal to the pixel value. For example, here we have the pixel value 109, then there are only 109 ones in the vector, and all the remaining bits are 0. The method gets its name because the encoded vector is just similar as a thermometer. Good thing about it is that now each bit in the encoded vector has a uniform associated weight. We again compute the convolutions in the first layer using both floating point weights and the binarized weights. But this time we use thermometer encoded inputs. We want to check the correlation of the convolutions again. And from the figure, we can see that the dots are pretty close to the diagonal line. output features computed with binary weights are highly correlated to the ones computed with floating point weights. The Pearson correlation coefficient is now 0.88, indicating a high correlation. And surprisingly, this time we do not observe any accuracy degradation after binarizing the input layer. We think that thermometer encoding helps with preserving the output feature similarity. Hence, it preserves the model accuracy. Okay, now we start to think about trading a bit of efficiency to improving the accuracy. We adapt our previous work, precision gating for BNNs, and use a fractional bit width. The idea is that some features in the network are more important than others, so we want to update them to a higher precision. Here's an example showing how it works on a convolutional layer. Instead of storing 1-bit feature maps, we maintain them in the memory in 2 bits. The blue circles here represent the 2-bit precision. We split the input activations into 1-bit MSB and the remaining 1-bit LSB. And first, there is a base phase, where we use the MSB activations to compute a regular binary convolutional layer and generate a partial sum. The partial sum represents the importance of the output features. We then use threshold delta to gate the partial sum to predict important features. And this generates a binary Musk tensor. Note that each channel in each layer has its own gating threshold. And followed by the base phase, there is an update phase. We do a sparse update using the Musk and increase the precision of those important output features. The sparse update are still binary convolutions. And finally, we combine the results from both paths and generate the output features. The good thing is there are only binary convolutions involved in this process, so we can still compute them efficiently using exclusive NOR plus pop count operations. And the gating thresholds here are trainable, so we don't have to manually do a lot of tuning. We test this fractional bit width idea on the CFAR10 dataset as a proof of concept. In our experiments, about 40% of the activations are updated to 2 bits, so the equivalent activation bit width is 1.4, and we use 1-bit weights. We observed that with fractional activations, our BNN achieves the state-of-the-art accuracy among different ResNet20 BNN variants, higher than the previous state-of-the-art IRNet. Its accuracy is also about 2% higher in terms of absolute difference than ReactNet, which is the model we are building on top of. Note that 1% improvement is already considered significant in ML community. The FracBNN also has a very low model size because ResNet20 itself is a lightweight model. So empirically, fractional activations substantially improve model accuracy. In this work, we have also proposed a new ReactNet model variant. We add an additional batch norm layer in the model to balance the number of plus and negative ones in the feature maps. It shows better model convergence. Please refer to our paper for details if you are interested. We combine the binary input layer, the fractional convolutions, and the new model variant, and test our FracBNN on the ImageNet dataset. We observed that FracBNN surpasses state-of-the-art BNNs and low-bit network designs by a large margin. It, for first time, achieves MobileNet V2 level accuracy with a competitive model size to those 8-bit compact network designs. So overall, FracBNN achieves a favorable trade-off between accuracy and model size. After verifying the efficacy of FracBNN, we implement the entire network accelerator using high-level synthesis and deploy it on Xilinx Ultra96 V2 board. The accelerator architecture is shown on the left. For each layer, we fetch the intermediate feature maps and the weights from the DDR memory, and then pass them to the fractional convolution engine. And after computing the shortcut, we transfer the output feature maps back to the DDR. And here is how we implement the fractional convolutional layer. We first implement a regular binary convolution. For each input feature maps, we parallelize along the filter dimension and it generates a sequence of partial output channels. This helps us alleviate the load and balancing problem. We then pipeline the computation in the other dimensions. We're able to achieve pipeline II1 in this case. In a binary convolution engine, there's also an enable signal that starts the pipeline. For the base phase, the enable signal is always on since we are computing a regular binary conv layer. In the update phase, the binary conv engine only computes those output features that exceed the threshold in the pipeline. It's worth mentioning that all the conv layers, including the input layer, share the same convolution engine, and all operations are binary max. Let's also take a closer look at the memory management of our ImageNet design. Since the DDR transactions are very expensive, we want to reuse the data as much as we can. For each output tile, the 2-bit feature maps and the weights are reused by the fractional convolution engine for many cycles. In contrast, the shortcuts are 4-bit and are only needed at the completion of each tile, which is much less frequent. So to reduce the DDR transactions, we store the entire 2-bit intermediate feature maps and 1 tile of weights in the on-chip VRAM. In the meantime, we transfer the 4-bit shortcut connections back to the DDR and only load them when necessary. In this way, the most frequently accessed data are maintained on-chip, and the less frequently used data are stored off-chip, where the capacity is larger, though transactions are more expensive. Since in the ImageNet design, we have to store the shortcut connections off-chip and transfer them back and forth within each layer, we want to minimize the communication overhead brought by these memory transactions. To achieve this goal, we use burst data transfer. We pack 512 bits together and transfer them at one time. In this way, we fully utilize the bandwidth of this device. We also want to mention that this happens only for the ImageNet accelerator. In the CFAR10 accelerator, everything is stored in the VRAM. We managed to unroll the entire design on device, so there's no data transfer between the accelerator and the off-chip DDR memory. We then evaluate the frame rate of both designs. For the CFAR10 accelerator, we observe that FracBNN has an approximately 16x speedup over the previous most accurate FPGA CFAR10 accelerator. FracBNN is also slightly more accurate in this case. And compared to RevNet, the one with the highest frame rate, our FracBNN accelerator achieves a 1.4x speedup with about 2% accuracy improvement. Here's the resource utilization of our design. It's worth mentioning that the DSPs are mainly allocated for batch norm, index calculation, and activation function. So from the table, we could see that FracBNN achieves both higher accuracy and frame rate. For the ImageNet design, we observe that FracBNN achieves a slightly higher frame rate compared to a prior low-bit network design, Synergy. But our model is 3.5% higher in top 1 accuracy. And compared to the FIN, which has a very high frame rate, our model is 21.5% more accurate, which is more suitable for practical usage. In the resource utilization, still, the DSPs are mainly allocated for batch norm, activation function, and index calculation. So overall, our FracBNN ImageNet accelerator achieves high accuracy and shows a real-time classification ability. The takeaway points from this presentation are: 1, we follow an algorithm hardware co-design approach. The FracBNN model is designed to be hardware aware and FPGA efficient. 2, for the first time as a binary neural network, FracBNN achieves MobileNet V2 level accuracy. We find that thermometer encoding can help us binarize the input layer. And on the accuracy side, fractional activations can substantially increase the BNN accuracy. So both of these techniques are FPGA efficient. 3, FracBNN Accelerator demonstrates a real-time image classification ability on embedded FPGA. And finally, our FracBNN is open sourced on GitHub. Feel free to check it out. Thanks for listening.